Welcome to lecture 9.5. Okay, I'm going to do another example. I'm going to use theorem 3 to graph out what McKelvey-Palfrey called the pi star relationship. So recall, here's theorem 3. Okay, for almost all games, pi star, the vector of players' probabilities, is odd for almost all lambda. Okay, and then the graph of pi starts the unique branch at the centroid. Okay, blah blah blah. Um, now, by the way, so I made this little graph here. Um, okay, that is not the ox game. Okay, the ox game. So the key is number 3. The graph. Look at pi star contains a unique branch. Wait. Wait. God, I guess. You know what? I guess. Darn it. It's not in theorem 3, but I've been thinking this. When lambda approaches infinity, this is true. I don't think it's been proven. That when lambda equals infinity, all the graphs in that pi star approach one of the Nash equilibria. Okay, so what's going on now is that the ox game, so it's matching pennies, and matching pennies only has one Nash equilibrium. It's the mixed strategy equilibrium. Okay, so that means that pi star graph, at least at the end, as lambda approaches infinity, is going to be only one branch. Okay, in particular, actually, I can show you what it looks like. Okay, this is it. This is page 29 from McKelvey-Palfrey's paper. So this is the ox game. Now, it has two branches. So the first one is A1. So this is like when I was graphing out P star sub A comma A1. That's what this is. This little squiggly line, this function right here, is what that is supposed to be. Okay, so ignore this for the moment. And by the way, this pi star in theorem 3, now that I think about it, I think McKelvey-Palfrey might have made like a typo or something. That pi star, I think what it should have is it should have a sub I. So it's pi star for player I is odd for almost all lambda. Okay. And they didn't say that. Instead, that pi star is a vector for all the players. I don't think that makes sense. I think it should have been, when they write the theorem, what they mean it is the pi star for any one of the players. So what I think the pi star I, okay, looks like this function right here. Okay, now pi star for player B looks like this one. Okay, now in both cases, so pi star for player 1 is just a line, and notice that it's for each value of lambda, there's only one branch. Okay, so it's odd. So that verifies theorem 3. It's odd. Okay, and a note also, it starts at the centroid here. So this is when lambda equals 0, the P star A, okay, equals 0.5. Is that right? Yeah. And same thing for P star B. Okay. So this is consistent with that part 3 of theorem 3. It starts at the centroid, and then as lambda approaches infinity, it approaches the Nash equilibrium. And I said for that game, for player A, the Nash equilibrium would be such that A mixes with 50-50 probability. And I said the mixed strategy equilibrium for player B would require B to mix with 80-20 probability. And so notice that branch for P star sub b1, as lambda approaches infinity, that graph has an asymptote at 0.2. If you look real close at the graph, you might need to look at your own paper for this. Okay, so that is consistent also with part 3 of Theorem 3, Kelvin-Pelfrey's Theorem 3. Okay, so but if you look at both players, if P star is supposed to be for both players, P star has 2 branches, so that can't be odd. So I think what McKelvey-Palfrey meant to have is a sub I, say P star sub I for any given player has got to be odd for almost all lambda. And so in this ox game, it equals 1 for all lambda. Okay. Okay, that was point 1. Now, here's what I want to do next. Is I want to show you the same thing. I want to demonstrate Theorem 3 for a different game. Okay? And the different game is the Battle of the Sexes game. Okay, so now let me explain. The Battle of the Sexes game. Okay, here's how it works. Okay. So, suppose there Battle of Sexes, there's a male and a female. Okay, and so now a female, and this is like a couple that's dating or they're married. And the idea is that each one has 2 actions, 2 possible actions. They can go to a movie or a play. Okay, so the male can go to the movie or the play. And here's one possible payoff that's kind of classic. So if they both go to a movie, the male gets a payoff of 4, the female gets a payoff of 2. Meanwhile, if they go to different things, if the male goes to the play and the female goes to the movie, they're not together. They want to be with each other, so they both get 0. Meanwhile, if the male goes to the movie, female goes to the play, here again they get 0. But if the male goes to the play and the female goes to, if they both go to the play, the male gets 1, the female gets 3. Okay, now, here's what I want you to see. So I told you didn't have to know game theory for this class, but you had to be ready to read Wikipedia to understand it. Okay, you're on your own. You've got to learn this through Wikipedia or somehow. That this game, first it has 2 pure strategy equilibria. One of those pure strategy equilibria is movie. Male goes to the movie, female goes to the movie. Okay? So you can see, if the equilibrium god says movie, the male says, okay, the female's going to the movie. Do I want to go to the movie or play? Well, I get 4 or 0. I prefer 4, so I'll go to the movie. Female says, well, if the male's going to the movie, as the equilibrium god says, I can go to movie and get 2 or play and get 0. I prefer the movie, so I prefer to do what the equilibrium god says. Okay, so that is a pure strategy equilibrium. Okay, now another pure strategy equilibrium is play. Okay, so you can verify it the same way. If the equilibrium god says both of you go to a play, then the male says, assuming the female's going to the play, I want to go to the play. But assuming the female is following what the equilibrium god says. Okay, the female says, okay, assuming the male is following what the equilibrium god says, okay, my best strategy is indeed to go to the play. So I want to follow what the equilibrium god says, so it's indeed in equilibrium. Okay. Notice it's two equilibria. Notice the male prefers this equilibrium, female prefers that equilibrium. Okay, that's kind of interesting. Now, here's what also is interesting. Turns out that this game has a third equilibrium. It's a mixed strategy equilibrium, and this is where the male randomizes between movie and play, and the female randomizes between movie and play. Okay, now we've got to pick these randomizing probabilities just right, okay, to make it an equilibrium. Now, I want you to look this up in Wikipedia to learn how to compute a mixed strategy equilibrium, so you're more familiar with this. But the key is, if the female is going to be randomizing, she must not have any strict preference over movie and play. She must be indifferent between going to movie or play. Otherwise, she would not want to randomize. She would want to pick one of them for certain, the one that gives her higher utility. But if they both give her the same utility, she's willing to randomize. Okay. Same thing goes for the male. Okay. So now here's how the mixed strategy equilibrium works. So the equilibrium god has to pick a probability for the male to go to the probability movie, probability play. The male has to randomize just so, in just such a way as to pick a probability just right so that the female is indifferent between movie and play. Okay. So now, here's what we're going to do. So we're going to figure out first what that probability must be. So, okay, here is P equals probability male goes movie. Okay. So now, if that's P, okay, now let's think about the female's payoffs, okay? So the female's utility, the female's utility for movie, if she picks movie, she gets 2 if the male has picked movie. So the probability of that is P. So her expected payoff is 2 times P. Okay, now if she goes movie. Meanwhile, it's if the male picks play, her payoff is 0. So it's plus 0 times the probability that the male picks play, which is 1 minus P. Okay, and then next, UF play equals, okay, so if she picks play, it equals 0 times the probability that the male is picking movie plus 3 times 1 minus P. Okay. And tell you what, I'm not going to do the arithmetic here or the algebra. Okay, so you can solve now. And then the final thing is you say, well, we have to for P to be part of an equilibrium, the female must be indifferent, so we must set these two equal to each other. Okay, those two utilities equal to each other. So we set 2P equal to 3 times 1 minus P. And what we get is P must equal 3/5. Okay, so for the mixed strategy equilibrium, the male has to be choosing a movie with probability 3/5. Okay, now let's set Q equals probability female goes movie. Okay, now let's think about what Q must be. Let's see, let me adjust this a little bit so you can see the whole whiteboard. Okay, so what we must have is U male movie equals the male goes movie. It's 4 times probability that the female goes movie, so it's 4 times Q plus 0 times 1 minus Q. And then U, M, play equals 0 times Q plus 1 times 1 minus Q. Okay. And did I get that? Okay. So now Q must be set so that the male is indifferent between either action. So we've got to set those utilities equal to each other. And so that implies that Q equals, okay, I'm going to skip the algebra, equals 1/5. But you can do this on your own. 1/5. Okay. All right. So probably male. Q is probably male. Goes movie is Q. All right. Now, let's graph. By the way, I forgot to mention this. So, when McKelvey-Palfrey, when they did this graph, they get that basically just by filling in. So you take that spreadsheet I did, I think in the last video, and I tried it with lambda equals 0, lambda equals 0.2. So Kelvin-Palfrey, you just got to try it with a whole bunch of different lambdas and fill that in, and that's how you get those graphs. Okay, that's what they did. Okay. Now, let's suppose that we did the same thing for this Battle of the Sexes game. Okay. If so, and then we would have, so I called it Q. Q is the probability that the male picks movie, and let's say, call it Q of lambda, call it Q star, okay? And just as we did before, when I called it PA1 star, so I said what we're looking for is a case where PA1 is, it's like the seed value, and then you plug that in, and then you get a sigma when both players optimize given the seed values, the PA1 and PB1. And then you keep on adjusting the seed values until the P's equal the sigmas. Remember that? Okay. And if you can do that, you've found an equilibrium. You've found a QRE, quantum response equilibrium. Okay. Now, the PA1 star and PB1 star that's going to work, it's going to depend on lambda. It's going to be various functions. And then that was that graph I just showed you. That shows the graph. Okay. Now I'm going to do the same thing this for Q star. So I'm going to call Q star. So we'll pick a Q and a P. So probably male goes to the movie. P, probability that the female goes to the movie. And then from those, we could compute the sigmas, the male's optimal response, sigma M, sigma F, the female's optimal response. And we're looking for a Q and a P such that the sigmas equal those Q and the P's, okay? The sigma M equals Q and the sigma F equals P, okay? If we found that, we're going to call that Q star and P star. Okay, so that's the equilibrium, the seed values that work. Okay, that's the idea. All right, now, first of all, okay, let's graph and we use theorem 1, this Q star lambda. Okay, now first off, that uses that theorem 3. So lambda goes from 0 to infinity, and then Q has got to be between 0 and 1. Now we know that when lambda equals 0, that's the case when both players just completely randomize. They pick their actions completely randomly. They pick each action with equal probability. And so what that means is Q has to equal 1/2 when lambda equals 0. So we know we've got a result there. Okay, and now, you know what? I guess theorem 3 doesn't say this, but I was thinking it did. But it also turns out that when lambda approaches infinity, the result is going to be the Nash equilibrium. Okay, the regular Nash when we don't use this QRE stuff. Okay, and so the regular Nash, there were 3. There were 2 pure strategies. 1, it was movie. 2, it was play. Okay, with those 2, and the first one, Q star equals 1. Okay, the male goes to the movie, both of them actually, Q star and P star equals 1. They both go to the movie with probability 1. And the second one, where they both go to the play, Q star is 0. Okay, so what that means is when lambda is infinity, we're going to have a graph, call a branch of that, call it pi star, but I'm going to call it Q star of lambda, such that it approaches 1, okay, when lambda is very, very big, and then also when lambda is very, very big, this Q star is going to have another branch approaching Q star equals 0, okay? And now the third case, when lambda is very big, it's going to approach the third equilibrium, and that was that mixed strategy equilibrium where Q star equaled 3/5. Okay, so 0.6, and I don't know where it started. If it started from here and goes up here, or here and goes down there, I'm not sure what it does. But either way, when lambda approaches infinity, we're going to have a third branch that approaches 3/5. Okay, then we're going to have one branch that starts off at the lambda equals 0, Q star equals 1/2. Okay. Now, I don't know what it looks like in between, okay? But the theorem 3 gets us started. It says, okay, it's got to start off with one branch here, okay? And then I guess theorem 3, I was mistaken. I thought it said that it's got to approach a Nash equilibrium at the end. So I think it's in the paper somewhere. Now it's escaping my mind. I was thinking it's theorem 3, but now maybe not. So anyway, the graph, what McKelvey-Palfrey called pi star, and I think should have been pi sub I star, for I represents one of the players. And so I'm calling it, for this Battle of the Sexes game, I'm calling it Q star. So this is for the male. This is now the final point of theorem 3 is it says that this one branch that begins at the centroid, and then it has to connect with one of these 3 equilibria. It says it approaches, when lambda approaches infinity, it approaches the limiting case of one of the Nash equilibria. Okay. Now, which one does it? Okay, I'm not sure, but let me go back to this. Okay, side note. McKelvey-Palfrey, most people will recognize this as an econometric paper. So what this does is it looks at some of the theory, previous experimental games, and tries to explain the results better. It looks at the data and comes up with a statistical model that explains the results better. Okay? So that's the main contribution of their paper. But it turns out there's another contribution that's completely pure theory. So it has to do with just game theory. It has nothing to do with statistics, econometrics, estimating stuff. And this is that they call it the QRE refinement. So a refinement is something in game theory. It says when there are multiple equilibria, that's a problem in game theory because we don't have a prediction. If there's multiple equilibria, like usually we like to say the Nash equilibrium is our prediction. But if there's multiple equilibria, what's the prediction? He said, well, it's ambiguous. Well, sometimes what game theorists do is they will do something called a refinement, and that's some notion that selects among the multiple equilibria. It says which one makes the most sense, something like that. So McKelvey and Palfrey have that. So what people call the QRE refinement, it selects one of the equilibria, and usually, usually it picks the one that seems to make the most sense. I think every case I've seen ever, the QRE refinement picks the equilibrium, the Nash equilibrium that makes the most sense. Okay, I haven't defined the most sense, but what Tim Grosclose feels seems right. Okay, that's what I mean by the most sense. So let me tell you this. I think that's what's going to happen. And the QRE refinement, what it is it's the branch that starts at what they call the centroid, the one where lambda equals 0, and it starts at the value of the probability where they're all randomizing equally. So in this case, it's going to be start at the 0, 1/2 dot, and there's going to be a single branch that goes from there, and it is going to meet up with one of these three branches. And which one of those it meets up with is one of the Nash equilibria, represents one of the Nash equilibria, and that's what the QRE refinement selects, that the Nash equilibrium representing by these three cases. All right, now let me go back to the game. Okay, what equilibrium makes the most sense? Okay, let me say what I think. I say, look, I think it's this one. So, by the way, the mixed strategy I don't think makes much sense because there's always a probability that they end up going to different places. So if they're both mixing, they're both picking randomly, there's a chance that the male's going to go to play and the female's going to go to movie, or the opposite. So that doesn't seem like the equilibrium that makes the most sense. Seems like it's got to be one of the pure strategy equilibria. The one to me that makes the most sense is movie. And I think the way it would go, for instance, if I were playing this with my wife, I would say, look, and by the way, she prefers plays. I do prefer movies. I would say, look, if you think play is what we should do, look, if instead we went to movie, I gain 3 utility points. You only lose 1. Therefore, it makes more sense for me to get my way. I don't think she would buy it, but in my mind, that's what makes the most sense. And I'm pretty sure, so I haven't worked this out, but I'm willing to bet that this QRE refinement, it selects this one. It selects the Q star equals 1, where the male goes to the movie. And that represents the pure strategy equilibria, where it's movie. Okay, so I think that third graph's going to look like this. These two, we know they look like this. Now, they can't look like that, because if so, that would mean in this area of lambda, there are 2 branches. There's an even number of branches. So that can't be. Okay. So let's erase this. Oh my gosh, my wrist is hurting. So it could look like this. Let's say a point, they begin at the same lambda. The other possibility is that they meet at the same point like this. And if so, that would be one single point where there are 2 branches. And we said that it said that it's got to be for almost all values of lambda. uh, that there's an odd number of branches, and this would be the set of zero measure where that happens. Okay, so that is what the Q star graph looks like. We could also graph the P star graph, what the female's probability would look like, and I think it would look very similar, except its centroid, the P star. Oh, it also would go to 1 because I think the Nash equilibrium that makes most sense also has the female going to the movie. So I think if we did the P star of lambda, it would look very similar to this. Okay, so that is theorem 3. Let's see. Okay, I think I've got. Okay, I think I did. Okay. Let's see. One final point. Okay. Let me explain. One little final point. So now, if you recall, theorem 3 says that it says for almost all games. Okay, not all games, but almost all games. And this is speculation, but I'm pretty sure I'm right. What would be a case where it would not be true? Okay, so the set of zero measure cases where it would not be true. Well, I think the answer would be where all we do is we pick the payoffs so they're just right. And I said, so this one, notice that you gain 3. The male gains 3 if you go from here to here. The female only loses 1. What if instead, oh, darn. This marker, I think, ran out of ink. What if instead we change that 3 to a 4, change that 1 to a 2. Okay, you see that? So notice what I've done. I've made it the exact opposite, the exact mirror image of it. So I chose this to exactly be the opposite of that. So I chose them just right. So I had to fine tune these payoffs. And if I do that, I think then all of a sudden theorem 3 would not work. It would be one of those zero measure cases where it doesn't work. Meanwhile, if instead I'd made that 4.001, okay, made it so it wasn't just right, then theorem 3 would work, okay? So that's the idea. If you can fine tune the payoffs just right, you can make theorem 3 not work. And that's where they get the almost all case, okay? Okay, so that is the final set of points, except what I'm going to do now is talk about assignment 6, and I'll give you some tips on how to do that. Or you're going to, trust me, I think from assignment 6, you'll really start to understand the QRE model better. Okay, so I will do that. See you there in the next lecture.